Hello everyone. Good evening everyone. Good evening. Good evening. So, am I audible and visible? Please let me know. Am I audible and visible? Good evening. Good evening. Good evening. Okay. So let's start. Let's start today's session. So beta, in last class, we discussed about the surface tension, correct na? In previous class, we discussed about the surface tension concept, and also we discussed about some very important consequences of the surface tension, right? Especially the calculation of the pressure difference in the liquid droplet or soap bubble or cylindrical jet. So these cases are very, very important cases as per the competitive exam point of view, right? You are getting numerical question, right? You are getting directly numerical question from this concept, right? The pressure difference, delta P, inside pressure minus outside pressure, or you can say concave side pressure minus convex side pressure, that is equal to sigma into 1 upon r1 plus 1 upon r2, right? That is a Young's Laplace equation, right? So we discuss about Young's Laplace equation. Young's Laplace equation. We discuss about Young's Laplace equation. Young's Laplace equation. And what is the Young's Laplace equation? What is the Young's Laplace equation? Okay, so if you consider interface like this, right? So this is the center of curvature for this interface. So we can say, right, let us consider this is the O1 and this radius of curvature, that is R1. And for this one, this is the center of curvature. Let us consider this is the O2 and this is the radius of curvature, that is R2, right? So we can directly write in this side the pressure is Pi, in this side the pressure is P naught, right? So Pi minus P naught, or simply we can say that delta P is equal to Pi minus P naught is equal to, this is sigma 1 by R1 plus 1 by R2, 1 by R1 plus 1 by R2, right? Where R1 is a radius of curvature for this interface and R2 is the radius of curvature for this interface, right? Now, this is a generalized mathematical expression. And if I'm talking about the liquid jet, right, liquid jet, or you can say, right, air bubble inside a liquid, in both the case you are getting the same mathematical expression. Air bubble in the liquid, you can say like this also, air bubble in the liquid, right? So liquid droplet or air bubble in the liquid, in both the case you are getting the same mathematical expression. And what is that mathematical expression? That delta P is equal to, right, that is 2 sigma by r. So let us consider this is your liquid droplet. and the diameter of this liquid droplet, let us consider that is d, right? In this side the pressure is P naught, in this side the pressure is Pi. So Pi minus P naught is 2 sigma by R. Is it okay now? So this is the first case. This is the first case. This is the first case. Now come to the second case. The second case is a soap bubble. That second case is a second important case is a soap bubble. And in case of the soap bubble, what is the delta P? The delta P is 4 sigma by R, right? 4 sigma by R. And third important case is the liquid jet. Third important case is a liquid jet. And in case of the liquid jet, what is the delta P? The delta P is sigma by R, right? In case of the liquid jet, what is the delta P? The delta P is sigma by R, right? So we already discussed these things. Okay. In last class, we also discussed about the surface energy, right? We already discussed about the surface energy concept. Surface energy concept. So surface energy is nothing but the, it is a, you can say it is a surface required, it is a energy required to create a surface, right? Surface energy is simple, right? Energy required to create a surface, or you can say work done which is required to create a surface, to form a surface, that is called the surface energy. As simple as, right? So this is nothing but the surface, or you can say energy required or work done required, work done required to form, work done required to form a surface, work done required to form a surface, that is nothing but the surface energy, right? Or you can say, right, energy required to create a surface, that is nothing but the surface energy. Now if you know the surface energy concept, so you can define surface tension in terms of surface energy also, right? You can define the surface tension in terms of the surface energy also. So surface tension is also defined as work required to increase the surface area, work required to increase the surface area. So you can define the surface tension in this form also, right? This is a new definition of the surface tension. So that surface tension is equal to work done which is required to increase the surface area. So what is the unit? That unit is joule per meter square. So this is the another unit of the surface tension, right? Sometime that unit is asked in this form, right? What is the unit of the surface tension? So remember that unit of the surface tension is joule per meter square, and beta joule per meter square is nothing but the Newton per meter only, right? If you multiply with meter in numerator and denominator, then you are getting the joule per meter square, right? So this is the another unit of the surface tension. Fine. And also we discussed a very, very important case, right? Remember that work required during the atomization process. What is the work required? What is the work required? Work required in atomization process, or work required for splitting, work required for splitting a bigger liquid droplet, of radius capital R into n number of small droplets. this process is called atomization, right? This process is called atomization. So tell me what is the expression that you are getting? What is the expression that you are getting? You are getting expression like this, now, that work done is equal to, this is sigma multiplied by the surface area of the bigger droplet. Surface area of the bigger droplet. So we can write 4 pi r square into n to the power 1 by 3 minus 1. We are getting this expression now. We are getting this expression, remember. We are getting this expression, yes or no? Right, we are getting this expression that work done is equal to sigma multiplied by 4 pi r square into n to the power 1 by 3 minus 1. Right, so this is the expression, this is the expression of the work required for splitting a bigger droplet into n number of small droplets. Right, you are getting same expression now? Please check now, please check. I already discussed in the previous class. Fine, now come to the next property. Right, come to the next property, next fluid property, which is a capillarity. Come to the next fluid property, which is a capillarity. This is the property number 10. So what is a capillarity? Right, what is the capillarity? So beta, capillarity is nothing but rise or fall of a liquid in a narrow passage, right? Rise or fall of a liquid in a narrow passage when that narrow passage is dipped in a liquid. Right, so that is called the capillarity, as simple as. Right, what is the capillarity? So capillarity is defined as rise or fall of a liquid in a narrow passage when it is dipped in a liquid. Right, so some liquid has a property to rise and some liquid having a property to fall. Right, so which liquid having a property to rise and which liquid having a property to fall, right? That is based on the cohesive force and the adhesive force. So in the case of the capillarity, the two important forces come into picture. The two important forces come into picture. The first important force is a cohesive force and the second important force is a adhesive force, right? Two important forces come into picture. Cohesive force, and the second one is the adhesive force. So what is the cohesive force? So beta, we already discussed number of times. Cohesive force is nothing but the intermolecular attraction force between the same molecules. Right, between the same molecules, that intermolecular attraction force is called the cohesive force. We discussed number of times. Right, we discussed in a surface tension concept, we discussed in a viscosity concept, right? So we discuss in a surface tension concept, viscosity concept, right? So cohesive force, this is the intermolecular attraction force, between same molecules, right? That is called the cohesive force. Now what is the adhesive force? The second important force is a adhesive force. Now tell me, what is the adhesive force? So adhesive force is intermolecular attraction force between two different molecules, right? Intermolecular attraction force between two different molecules. So that is called the adhesive force, right? So let us consider there are two molecules of same liquid, right? So intermolecular attraction force between these two molecules is a cohesive force. Now let us consider there is a one molecule, right? There is a one molecule and there is another molecule, and both the molecules of two different substance, of two different substances. So intermolecular attraction force between these two molecules is a adhesive force, and this is cohesive force. Right? Now, if cohesive force is greater than adhesive force, then tell me, if cohesive force, there are two possibilities, beta. Cohesive force greater than adhesive force. There are two possibilities. Cohesive force is greater than the adhesive force. This is the first possibility. And there is a second possibility where adhesive force, the second possibility is where adhesive force is greater than the cohesive force. Right? There are two possibilities. The first possibility is cohesive force is greater than the adhesive force, and the second possibility is adhesive force is greater than the cohesive force. So beta, if cohesive force is greater than the adhesive force, right, in that type of liquid, right, where cohesive force is greater than the adhesive force, right, for example mercury, right, for example mercury, in such type of liquid where cohesive force is greater than the adhesive force, right, capillary fall occurs, right, capillary fall occurs. That means if you put a narrow passage in a mercury, right, then in that passage fall of mercury occurs, right. So when cohesive force is greater than the adhesive force, then capillary fall occurs, and the capillary fall is also called capillary depression. Capillary fall is also called capillary depression. So if you ask me example where cohesive force is greater than the adhesive force, so beta, very simple example, that is a mercury. Very simple example, that is a mercury. Right? Now, adhesive force is greater than the cohesive force. What happened when the adhesive force is greater than the cohesive force? So beta, when adhesive force is greater than the cohesive force, in such type of liquid, right, rise of the liquid in the narrow tube occurs, right. If you put a narrow tube in a liquid where adhesive force is greater than the cohesive force, then in that particular tube or in that particular passage, that rise of the liquid occurs. That is called capillary rise, right. That is called capillary rise. Right. And if you ask me example, so that example is nothing but the water. Simple example. Right. Now, tell me which liquid having wettability property and which liquid having non-wettability property, because that wettability property and non-wettability property of a liquid, that also depends on the cohesive force and the adhesive force. Wettability property and the non-wettability property. So it is simple. Wettability property means a liquid which weight a surface, right. So that liquid having wettability property, and if liquid does not wet a particular surface, then that liquid having non-wettability property. So your wettability property and the non-wettability property, right, also depends on the cohesive force and the adhesive force. So beta, it is very simple, right. If cohesive force is greater than the adhesive force, that means that liquid having, tell me, if you drop a mercury on a surface, so your surface is wet or not? If you drop a mercury on a surface, then your surface is wet or not? Tell me. So obviously your surface is not wet. That means mercury has a non-wettability property. Mercury has a non-wettability property. So we can say beta, when cohesive force is greater than the adhesive force, right? When cohesive force is greater than the adhesive force, such kind of in such kind of liquid there is a non-wettability property. Non-wettability property. Non-wettability property. Non-wettability property. So if someone asks you, right, capillary fall or capillary depression occurs in which kind of fluid or in which kind of liquid? So you can say a liquid having non-wettability property. A liquid having non-wettability property, in such kind of liquid that capillary depression or capillary fall occurs. Are you getting my point? Right? Are you getting my point or not? Right? And if adhesive force is greater than the cohesive force, if adhesive force is greater than the cohesive force, that means that liquid having wettability property. Right? If you put water on a surface, so definitely your surface gets wetted. So water having wettability property. Right? So in which kind of liquid having wettability property? A liquid where adhesive force is greater than the cohesive force. Such kind of liquid wettability property is there. Right? So wettability property is present. Wettability property. Wettability property. Is it fine? Okay. Now see beta, let us consider a surface. Let us consider a surface like this. Let us consider a surface like this. Let us consider a surface like this. Now in this surface, let us consider there is a water. Let us consider there is a water. Right? I drop water in this particular surface. So if you see the drop of water, so beta, your drop of water is spread like this. Your drop of water is spread like this. Your drop of water is spread like this. Whereas if you drop a mercury on this surface, so your mercury is like this. That mercury droplet is like this. Mercury droplet is like this. Tell me yes or no. This is a very common example, right? This is the water droplet, and this is the mercury droplet, right? This is the water droplet, this is the water drop, and this is the mercury drop. This is the mercury drop, right? Or better we can say a liquid in which adhesive force is more as compared to the cohesive force. In this case, adhesive force is acting between the surface and the water molecules, whereas cohesive force acting between the water molecules, right? So this is the H2O drop, and here that adhesive force is greater, or better simply I am writing adhesive force is greater than the cohesive force, right? Adhesive force is acting between the water molecules or water particle and the surface, whereas the cohesive force between the water molecules, right? So in this case adhesive force is more as compared to the cohesive force. In this case, that cohesive force between mercury molecules is more as compared to adhesive force between mercury and the surface. Is it fine? Okay. Now see, there is a concept of angle of contact. So if you draw a tangent like this, right, Here also, if you draw tangent from the point of contact like this, like this, right, like this. So this angle, better this angle from the surface, right, this is the surface. Now in an anti-clockwise direction, this angle is theta, and here from the contact from the surface in anti-clockwise direction, this is the angle theta, and that angle theta is called, that angle theta is called contact angle. That angle theta is called contact angle, right? That angle theta is called the contact angle. So tell me, in this case, theta is less than 90 or greater than 90? So it is clearly, right, it is very much clear, your theta is less than 90. Your theta is less than 90. Theta is less than 90. That means angle is ac-. Hello. Now it is fine. Is it okay? Okay. So we are here. Okay, so we are here. So a liquid, a liquid, a liquid having non-wettability property, a liquid having non-wettability property, we observe capillary depression, and a liquid having wettability property, we observe the capillary rise, right? So if there is a surface, if let us consider there is a surface, and if you drop liquid droplet, sorry, if you drop water droplet, and if you drop if you put a mercury drop, right? So this is the water droplet. Your water droplet is spread like this, and your mercury droplet is spread like this, right? And this angle is called the contact angle, right? So theta is a contact angle. So in this case, right, in this case, that theta value, in this case, that theta value is, in this case, that theta value is less than 90, right? Theta value is less than 90. That means a liquid having wettability property, that contact angle is the acute angle. Correct, na? Contact angle is a acute angle. Whereas a liquid having non-wettability property, whereas a liquid having non-wettability property, for such type of liquid, that theta value is greater than 90 degree. That means this angle is obtuse angle, right? So it is very simple. A liquid having wettability property, that theta is less than 90, acute angle, and a liquid for which, or a liquid having non-wettability property, a liquid having non-wettability property, the contact angle is greater than 90 degree, right? So I hope you can understand this. Okay, now to understand, just 1 minute, uh, just 1 minute, na? So to understand the capillary rise and the capillary fall, to understand the capillary rise and the capillary fall, let us consider a beaker. Let us consider a beaker like this. So this is the water beaker, right? This is the water beaker, right? This is the water beaker. This is the water beaker, right? So in this beaker there is a water. This is the water. This is the water. Now I am considering another beaker. Now I am considering another beaker, and this beaker is full of mercury. I am considering another beaker. Beaker number 2. And in this beaker there is a mercury, right? In this beaker there is a mercury. So this is the mercury. Right? This is the mercury, right? This is the water. So we know that in case of the water, that adhesive force greater than the cohesive force, right? Water having wettability property, contact angle is less than 90 degree. Contact angle is less than 90 degree. Right? Now come to here. In case of the mercury, the cohesive force is greater than the adhesive force between, right? Cohesive force is greater than the adhesive force. Mercury having non-wettability property. And theta is greater than 90 degree. Theta is greater than 90 degree, right? Now I am taking a small diameter transparent glass tube. Small diameter transparent glass tube, right? Now I am putting that small diameter transparent glass tube in water like this, right? So this is the transparent glass tube. This is the transparent glass tube, right? This is the transparent glass tube. And let us consider the diameter of this transparent glass tube is small d, right? This diameter is a small d. This diameter is a small d, right? Now we know that beta water has a wettability property, and we know that a liquid having wettability property, right, is tendency to rise on this particular tube. So if you observe, right, that water rises in this particular transparent glass tube, right, like this, right? Water rises in this particular glass tube, right? And this, see here to here, this is the capillary rise. This is the capillary rise, right? This is the capillary rise, and this is called meniscus, right? This is called meniscus. This is called meniscus. And if you see that meniscus, right, if you exaggerate this particular meniscus, so a liquid having wettability property or liquid rises in a tube if you see that meniscus is like this. If you exaggerate in meniscus part, so meniscus is like this. So beta, tell me, it is a concave meniscus or convex meniscus? It is concave meniscus or convex meniscus? Concave or convex? So obviously this is concave meniscus, right? In this case, that meniscus is concave meniscus, concave meniscus, right? Concave meniscus. Fine. Now come to this beaker, So again I am doing the same thing. I am taking a small diameter transparent glass tube. So this is the small diameter glass tube, right? A small diameter glass tube. Now, since we know that cohesive force is greater than the adhesive force between the glass tube and the mercury molecules, right? So here that adhesive force is lesser, cohesive force is more. So in this case you observe fall like this, right? So here to here, here to here, that is a H, right? So in this case that H is a capillary rise, in this case that H is a capillary fall. And if you see the meniscus, right, again this is the meniscus, this is the meniscus, right? So tell me, what is the meniscus? What is the shape of the meniscus? Concave or convex? Concave or convex? So obviously beta, that meniscus is convex meniscus, right? So this is liquid having wettability property, this is liquid having non-wettability property. So if you put a narrow passage, or if you dip a narrow passage in a liquid having wettability property, you observe such kind of rise, that is called the capillary rise. And a liquid having non-wettability property, right, you observe drop, such kind of drop, and that is called capillary depression or capillary fall. Right. Now if I am talking about the mathematical expression of H, right, if I am talking about the mathematical expression for the capillary rise or capillary fall, so beta, mathematical expression is same in both the case. You will get the same mathematical expression, right? In both the case you are getting the same mathematical expression, right? Now so here I am deriving the mathematical expression for the capillary rise. Same mathematical expression is applicable for the capillary fall also, right? Now beta, see, capillary rise or capillary fall, mathematical expression for capillary rise, mathematical expression for capillary rise or capillary fall, capillary rise or capillary fall, that is H, right? So to understand the mathematical expression, again I am considering a beaker, and in this beaker let us consider water is present, right? So this is the beaker, right? This is the beaker, and in this beaker let us consider water, right? So this is the water. This is the water. Right? Now, this is the narrow or small diameter glass tube. This is a small diameter glass tube. Small diameter glass tube. This is a small diameter glass tube. Small diameter glass tube. This diameter is small d. This diameter is small d. Now, water rises in this tube, and if you see the meniscus, that meniscus is like this, right? If you see the meniscus is like this, right? This is the concave meniscus, and this is H, correct? Na? This is H. This is H. This is H, right? And surface tension is acting like this. Right? This is sigma. This is surface tension sigma. This is sigma, and this angle is the theta. This angle is the theta. Fine. Now, I want to calculate this H. Na? I want to calculate this H. So, beta, this is very simple, right? At the equilibrium condition, the weight of the water which rises up to height H is balanced by the vertical component of the surface tension force or not? Tell me. At the equilibrium, at equilibrium condition, the weight of liquid, right? In this case, there is a water. Weight of liquid rises up to height H, This weight is balanced by the vertical component of surface tension force or not? Tell me. Vertical component is balanced by vertical component of surface tension force. Vertical component of surface tension force. Tell me yes or not. Tell me yes or no. Yes. That weight of the liquid rises up to height H. This weight, right? This weight, right? Obviously, this weight is balanced by the vertical component of the surface tension force. So first calculate the weight of the water, beta. First calculate the weight of the water which rises up to height H. So what is the weight? So weight, for calculation of the weight, this is the weight density multiplied by volume. Weight density multiplied by volume. We know now weight density. Let us consider gamma is the weight density of liquid. Weight density of liquid. Weight density of the liquid, and weight density is equal to, this is weight per unit volume. Weight per unit volume. So we want to calculate the weight. So this is weight density multiplied by volume of liquid which is rises up to height H, right? This is equal to the vertical component of the surface tension force. So first calculate the vertical component. So if you calculate the vertical component, right, if this is the theta, this is also theta, and this component is the sigma cos theta, and this component is the sigma sin theta. We need the vertical component. So vertical component is sigma cos theta. But this is not the force. This is the surface tension. This is the line force per unit length. We want to calculate the surface tension force. So multiply, this is the surface tension force per unit length. We want to calculate the surface tension force, right? So multiply by with length where the surface tension acts, right? So where the surface tension acts, so beta, if you see from the top, so it is very much clear. If you see from the top, then it is very much clear. The surface tension is acting like this. Surface tension is acting like this. That means in a periphery, right? In a periphery, or you can say in a circumference. Tell me yes or no. If theta is equal to 0, then that is a vertical. No? If theta is equal to 0, then that is a vertical. So your surface tension is acting like this. So this is the surface tension per unit length multiplied by with length where surface tension act. So this is sigma cos theta multiplied by pi into d. Sigma cos theta multiplied by pi into d. Sigma cos theta multiplied by pi into d. Is it fine? Okay. Now, this is the gamma, or simply better you can write rho into g into volume. Right? Which volume? This volume. So what is the volume of liquid which is rises up to height h? So this is pi by 4 d square into h is equal to, this is sigma cos theta pi d, right? Now see, pi and pi is cancel out, d is cancel out. So ultimately you are getting that h is equal to, this is the 4 sigma cos theta divided by rho g d, or you can say this is the 4 sigma cos theta divided by, this is gamma into d. So this is the mathematical expression of capillary rise or capillary fall. This is the mathematical expression of capillary rise or capillary fall, right? 4 sigma cos theta by rho into g into d, right? And if you see this mathematical expression, then it is very much clear your capillary rise is inversely proportional to the diameter, right? Your capillary rise or capillary fall h is directly proportional to 1 by diameter. So if you want to see the capillary rise or capillary fall, right? If you want to see the capillary rise or capillary fall, so your tube diameter must be as minimum as possible. Then it is possible to see the capillary rise or capillary fall by the naked eyes. Otherwise it is not possible, right? It is very much clear, if d is more, if diameter is more, then h is less. If diameter is more, then h is less. So if you want to see capillary rise or capillary fall by naked eye, then definitely your diameter should be as minimum as possible, right? And as a thumb rule, right, as a thumb rule, the diameter must be less than 10 to 12 millimeter. This is the thumb rule, right? Actual diameter you can calculate from the data that is given, but as a thumb rule, if you want to see the capillary rise or capillary fall, so the diameter must be less than 10 to 12 millimeter, right? Fine. Now, right, beta, I already told you this expression is applicable for the capillary rise also and the capillary fall also, capillary rise as well as capillary fall, right? Now we know that in case of capillary rise, in case of the capillary rise, what about the theta? What about this theta? Obviously this theta is less than 90 degree. In case of the capillary rise, that theta is less than 90 degree. Yes or no? Right? So if theta is less than 90 degree, this theta is less than 90 degree, that means this term, see, sigma is always positive quantity. Sigma is always positive quantity, gamma is always positive quantity, d is always positive quantity. right? So if your theta is less than 90 degree, then your cos theta is also positive quantity. So whenever capillary rise occurs, and you are using this mathematical expression, your H is positive. That H is positive, right? And when capillary fall occurs, in case of capillary depression, in case of capillary, in case of capillary fall, the theta value is greater than 90 degree. The theta value is greater than 90 degree, and theta value is greater than 90 degree, and we know that, right? Theta value greater than 90 degree. So this term, right, sigma positive, gamma positive, D positive, but this value is negative. This term is negative. So your H is negative. Your H is negative. Your H is negative. So you can use same mathematical expression for the capillary rise as well as for the capillary fall. Fine. Now, some important facts. In case of pure water, and clean glass tube, in case of pure water and clean glass tube, right? In case of pure water and the clean glass tube, the theta value is 0 degree. Theta value is 0 degree. So whenever you are getting a problem where water is mentioned, right? Whenever you are getting a problem where water is mentioned and theta is not given, especially you are facing such kind of problem in engineering services, right? In gate problem, theta value is given. If theta value is not given in case of the water, then assume that theta is equal to 0 degree. Assume that water is a pure water and your glass tube is a clean glass tube. So whenever problem is based on the water, right? So assume the theta value is 0 degree, right? So in case of the pure water and clean glass tube, the theta value is 0 degree. And in case of mercury, and clean glass tube, right? In case of mercury and clean glass tube, this value theta is approximately equal to 135 degree, right? In some books you are getting 135, in some books you are getting 136, in some books you are getting 138 also, right? So in case of the mercury and the clean glass tube, the theta is approximately equal to 135 degree, right? So these are the important facts. You must remember this. You must remember these important facts, right? And also to solve the engineering services problem, right? At least you know the surface tension value for water air interface. For water air interface, it is 0.0. It is 0. That surface tension value for the water air interface is 0.072 Newton per meter, right? And for mercury air interface, this value is around 0.48 Newton per meter, right? In case of the engineering services problem, sometime this data is not mentioned. So at least you remember this, at least for water air interface and the mercury air interface, you must remember these values. Fine. Now, so this is about the tube, right? This is about your narrow passage is a glass tube of diameter d. But if your narrow passage is formed by using two plate, right? Narrow passage is formed by using two plates, then how you calculate the H? The same mathematical expression is not applicable. This expression is applicable for a tube having diameter that is d. This expression is applicable for tube having diameter d. But if I'm talking about the let us consider the narrow passage is formed by using two plates, right? Narrow passage is formed by using two plates. So let us consider plate number 1 and let us consider this is the plate number 2, right? Plate number 1 and the plate number 2. These are two plates, correct? These are two plates. Like this. Fine. Okay. Right. This is the two plate. This is the plate 1. This is the another plate. Right. And your narrow passage is formed by using these two plate. And let us consider this gap is W. Let us consider this gap is W. Let us consider this gap is W. Are you getting now? Are you getting the problem now? This is the plate number 1, this is the plate number 2. This is the plate number 1, this is the plate number 2, and your narrow passage is formed by using these two plate. So this gap is W. This gap is W. Right? Now this narrow passage is dipped in a water. This narrow passage is dipped in a water. So let us consider this is the water. This is the water. Right? This is the water. This is the water. Right? This is the free surface. So here also you observe the capillary rise. Na? Here also you observe the capillary rise. Right? Here also you observe a concave meniscus like this. Concave meniscus like this. Concave meniscus like this. Concave meniscus like this. Right? So in this case, this is the H. Right? In this case, this is the H. Now, in this case, can you calculate the H? Can you calculate this H, this capillary rise? Right? Capillary rise or fall. Capillary rise or fall in case of two plates. In case of two plates. Okay, so try to calculate this. Capillary rise or fall in case of two plates. Try to find out in this particular case. So beta, logic is same, right? In this case, the surface tension is acting like this, right? Surface tension is acting like this. This is sigma, this is sigma, this is theta, right? This is theta. Is it okay? Now at equilibrium, the weight of the water or weight of the liquid rises up to height h is balanced by the vertical component of the surface tension force. So that logic is same. Weight of liquid rises up to height h is balanced by the vertical component of vertical component of surface tension force. Vertical component of surface tension force. Vertical component of the surface tension force. Right. So calculate the weight. So weight of the liquid rises up to height h. So weight density is gamma. Right. Weight density is gamma multiplied by volume. Volume of this liquid. So weight density multiplied by volume. And this is equal to vertical component of the surface tension force. So vertical component, that is a sigma cos theta. This is the surface tension multiplied by the length where it acts. So tell me what is the length? Tell me what is the length? Tell me what is the length? Because that is the only thing that is important. What is the length where the surface tension acts? Where the surface tension acts. So can I say L plus L? The surface tension, right? If you see this meniscus, your meniscus throughout the length L, if let us consider this length is L. Let us consider that plate length is L. Let us consider that plate length is L. Right? So if you see, this is the meniscus, right? And surface tension is acting like this. Tell me yes or no. Tell me yes or no. Is it clear to everyone? Is it clear to everyone? Is it clear to everyone? Tell me yes or no. This length is L. Right? This is sigma. Sigma, 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 sigma. Is it clear? So, beta, this is simple. This is 2 times of L. Right? L plus L. So, it is 2 times of L. 2 times of L. Right? Now, gamma multiplied by volume. So, gamma multiplied by volume. So, tell me what is the volume? What is the volume? H multiplied by W multiplied by L. H multiplied by W multiplied by L is equal to, this is sigma cos theta multiplied by 2L. Right? Now, L and L is cancel out, L is cancel out, and ultimately what you are getting, that H is equal to, this is 2 sigma cos theta divided by, right, gamma into W. Gamma into W. Right? What is the W? The W is a width or gap. What is the W? The W is gap between these 2 plates. W is the gap between the 2 plates. So this is the mathematical expression of capillary rise or capillary fall. This is the mathematical expression of capillary rise or capillary fall. Is it fine? And if we assume there is a one special case, and what is that special case? There is a one special case, and what is that special case? If W is equal to diameter, if you compare case number 1, let us consider this is a case number 1. Let us consider this is the case number 1. Let us consider this is the case number 1. Right? Let us consider this is a case number 2. This is the case number 2. This is the case number 2. So if you compare the case number 1 and case number 2 under this assumption where W is equal to, the gap between the 2 plates is equal to the tube diameter. Right? I am comparing the case number 1 and case number 2. So let us consider in case number 1 the capillary rise is H tube, and in the case number 2 the capillary rise is H plate. So we know that beta in this case this is the 4 sigma cos theta divided by gamma into D. In this case it is 2 sigma cos theta upon gamma into D. So we can easily comment, right? We can easily comment that H plate we can easily comment that H plate is equal to H plate is equal to H plate is equal to H tube divided by 2, right? So this is the direct question which is asked in your examination, right? That H plate, in the case of the plate, that capillary rise is equal to H tube divided by 2. Fine. Is it clear? Is it clear? Now come to the case number 3. Case number 3. Right? The case number 3 is your homework question. Try case number 3. Try case number 3. Case 3 is your homework question. Sir, what is the case 3? What is the case 3? What is the case 3? Find the capillary rise or capillary fall. Capillary rise or capillary fall. Capillary rise or capillary fall in a annular space, in a annular space of two concentric tubes, of two concentric tubes. Capillary rise or capillary fall in annular space of two concentric tubes. So this is the one tube, this is the one tube, right? And this is the another tube, this is the another tube. Right, this is the tube number 1, and let us consider this tube having diameter small d, right? And that outer diameter is capital D, right? Outer diameter is capital D. That this diameter is a small d and the outer diameter is capital D. And this is the narrow passage, right? This annular space, this annular space is a narrow passage. And if this concentric tube is dipped in a water, right? So let us consider this is the free surface of water, so obviously if water is there, so you observe the capillary rise, so capillary rise, you observe the capillary rise. So this is the capillary rise, right? So calculate this H, calculate this H, right? So case number 3 is your homework problem. This is your homework problem. So I already discussed 2 cases. Concept is same, right? Concept is same. At the equilibrium condition, balance weight of the liquid which rises up to H by vertical component of the surface tension force. So the concept is same, right? So this is your homework problem. So try this question, okay? So I hope whatever we discuss in today's class, that is clear to everyone. So in tomorrow's class, we will discuss some numerical problem, right? Tomorrow's class, we will discuss some numerical problem. So today we discuss about the capillary rise and capillary fall, and also mathematical expression, of H in case of in case of tube, right? Mathematical expression of H in case of plates, right? Next case is your homework problem. Okay, so I think this is enough for today's class. So I hope beta whatever we discuss in today's class, that is clear to everyone. And if you have any doubt, you can connect with me by Telegram, right? So whatever you have doubt, you can ask me in Telegram group also. Okay, fine. So thank you so much for today's class. See you guys in tomorrow's class. So bye bye, take care, and good night everyone. Good night.